Hello, so today our group gonna present about our celestial sphere. So the chosen location of our celestial sphere for our observer here is the pink little guy, the pink cute little guys. So the chosen observer for our location is at Geneva, Switzerland at the 46 degree north. So first we would like to explain our celestial equators and the ecliptics. So the celestial equator is the one here in the yellow strip, the line that perpendicular to the NCP. And the ecliptic here is the green plate one that has 23.5 over from the celestial equators. And now we move to define the vernal equinox. The vernal equinox here is the number 3 at here. And then when we move along the ecliptics, we move to get to the number 4, which is the summer solstice. And then we move to number 1. We got moved to the autumnal equinox. And then the last we move to winter solstice. And then we come back to number 2, so we come back to number 3, which is vernal equinox. And then the difference between daytime and nighttime in this season. So first is number 3 and number 1, both vernal and autumnal equinox. They both have the same. The length of the daytime and nighttime for them is the same. And for the winter solstice, the nighttime is longer than daytime. And the last for the summer solstice, the daytime is longer than the nighttime. And then we're gonna explain how does the sun rise and set in each season. So the first we're gonna move to number 3, which is the vernal equinox. So the vernal equinox here, the sun will rise exactly in the east, and then they will set exactly in the west. And this is applied with the number 1 here, which is the autumnal equinox. And the next is about the summer solstice, which is number 4 here. So the sun will rise at the north of east, and then will set at the north of the west. So the sun path they will across the sky is long and high. So it's the result that why summer solstice have longer daylight hours than the nighttime. And then the last with our number 2 here. So it is a winter solstice. So the sun will rise at the south of the east and set south of the west. So the sun path is short and low. So it's the reason that why winter solstice had the nighttime day longer than the daytime. And next we move to our next question, which is explain the reference point and reference plane of the equatorial coordinate system. So the first we begin with the reference plane. The reference plane is the celestial equator or the yellow strip here, which is the Earth equatorial plane that extends outward into the space. So it divides the celestial sphere into the northern and southern celestial hemisphere. So it's some kind like Earth serve as the same role as the Earth equator in geographic coordinate. And now we move to the reference point. So the reference point is here. So we go back to our number 3, which is the vernal equinox. So this is a point on the celestial equators where the sun crosses from the southern celestial hemisphere to the northern one in March. So all angular measurement of right ascension start from this point, which is here number 3 as the vernal equinox. And then we're gonna explain the meaning of declination. So declination is the angular distance of an object north or south of the celestial equator. So we're gonna measure the angular measurement distance from here, the celestial equator, from the yellow strip line. So it is measured along a great circle passing through the object and the celestial pole. So the value they will range from the plus 90 degree at the north celestial and can go up down to minus 90 degree at the south celestial pole. So declination is directly analogous to latitude on our Earth. Okay. And the last thing to our question number 3 is we're gonna explain our right extension, or in short term we call it RA. So the right extension is the angular distance measured eastward along the celestial equator from the vernal equinox point to the hour circle of the object. So the right extension they measure in hours, minutes, and seconds. So the 24 hours of the right extension they correspond to the full 360 degree circles. So 1 hour of the right extension is equal to 15 degrees. So if you mean that you move from the vernal equinox to here to the summer solstice, it means the summer solstice compared to the vernal equinox, they will have plus 6 hour right extension. And the autumnal equinox will have 12, the winter will have 18 plus 18, and they come back to the vernal equinox, which is the plus 0 hours. So it means that the right extension of RA they are analogous to the longitude of our Earth, but it uses the time unit in hours, minutes, and seconds because the Earth rotating. So the next mix will explain you about the question number 4, which is how to identify declination from an observer in horizontal coordinate system, and he will give the 2 examples.
Okay, well, so now I'm gonna explain how can we identify a star declination from what an observer see in the sky. And for the declination, it's like a latitude that, but for the celestial sphere. So it can tell that how far from the north or south an object is far from the celestial sphere. And you see a star that is across two meridians. It's meaning that when it is the highest point in the stars, we can estimate the declinations using these relationships, like altitude equals 90 degrees minus of the absolute values of latitudes minus declinations. And for this universe, our latitude is 46 degree north. And for these 2 examples, first the at Polaris, the North Star, we know that the Polaris has a declination close to plus 90 degrees, so it's almost exactly at north celestial sphere. And for Geneva, the Polaris will appear about 46 degrees above the north horizontal, as we all know. And for the second example, the star on the celestial equator, let's consider star with the declinations of 0 degrees. So meaning that it lies on the celestial sphere. And for the Geneva, the star will reach a maximum altitude at about 44 degrees. And the star will rise in the east and set at the west, just like the sun during the equinox, like the position 1 and position 3. Yeah. And for the last part, the circumpolar star, that it will never go below the horizontals. It will appear as a circle that travels around north celestial sphere, north celestial poles all night. And we will use this rule like star, which is the circumpolar, the declination is will greater than 90 degrees minus the observer latitude. So for Geneva, it's equal 44 degrees. So it's meaning that if the star has a declination greater than 44 degrees, it will be a circumpolar in Geneva. And Why the observer's locations matter to these? Because of if you move closer to the equators, the fewer stars will be circumpolars, and if you move closer to the North Pole, more stars will become circumpolars, and it will show that how your locations on Earth change what you see in the sky. And to conclude, like using our domes, celestial dome models, I can visualize how Earth tilts and rotations and how the orbits affects to the motion of sun and stars. And we can also know how the astronomers use the coordinates like declinations or right ascensions or any positions, the ecliptics or celestial equators, to locate an object on the sky. And we can also see how observer latitudes determine star visibilities and also seasonal change. Thank you very much for listening.